Welcome to the lecture series on soft computing in computer science. This presentation, what we are going to see is basic artificial neural network models. So the presentation outline is for the model that we have discussed in the last presentation, very particularly the very primitive model that was been introduced in the year 1943, that is Mekula and Pitts neuron model, followed by Hebb network, perceptron network, Adeline, Madeline, and then I wish to discuss you the problem of linear separability. And you should remember that for each model we are going to see architecture, net input calculation, output calculation, as well as weight updation. This weight updation is called by the name learning. So in general, when anyone asks about what is meant by learning in neural network, it is nothing but weight updation process. So let me go the topic one by one. The first model, that is Mekula and Pitts model. As I said in the presentation outline, for each model what we are going to see is architecture first. So if you look at the diagram in this presentation, it is a 2 input 1 output model. The inputs are represented by the name x1, x2, and each input has been carried out by the weight value w1 and w2. In case if this neural network model has bias, then the network model will have one more additional input connection x0 that will be associated with the bias term b. So the Mekula and Pitts model is shortly called by the name MP neuron, and it is the very basic primitive model that was being created during the year 1943, which has been widely used in designing logistic function, right. So next to architecture, what we should remember is, we should remember about the net input calculation. So what is the formula for net input calculation? That is Y in is equal to summation I equal to 1 to n xi wi. If you look at the diagram, I already say to you that, so you have to divide this node into 2 half, so that the one half is going to do the summation operation, another half is going to the threshold operation. So whenever I want to say that about the net input calculation, the net input calculation should be like this, summation I equal to 1 to n xi wi. In case if I add bias, some standard weight value, then the formula will be Y in is equal to B, that is bias, plus as usual that summation weighted sum value, right. So in this particular neuron, the activation function followed is a binary step function, that is we have a threshold value theta, over the theta and above what I can decide, and less than the theta and above what I have to decide. So that is the thing that I need to decide. If it is if the net input value, that is Y in value, if it is greater than or equal to theta value, then the output produced by the neuron should be 1. In case if the net input produced by the network is less than the theta value, then it is going to be 0. This is what the Mekula and Pitts neuron model is all about. So the architecture is 2 input and 1 output model. Not necessarily 2 input, we can have n number of inputs, that is a 2-layer model, input layer as well as output layer, 2-layer model. In input layer we can have n number of input nodes, and in output layer you have to have only 1 output nodes, and in the input layer you can have bias or you may not have bias. This is the optional connections. Based on the problem you can introduce the bias as well as no bias. Let me discuss why we need bias and all in the advanced lectures of this presentation. As of now, you need to understand that bias is some standard connected weight value to the network model in order to expect the desired output. So how to understand the working of this MP neuron? So let me give some examples. The first example is calculation of net input. Here the input connection is without bias. So given the network model, how many neural node input nodes are there? There are 3 inputs node are there. One input node is the input connection 0.3, another one is 0.5, another one is 0.6. for which the corresponding output connections are 0.2, 0.1, minus 0.3. So I can say this as a vector, that is input vector as well as weight vector. Input vector is x1, x2, x3, x1, x2, x3, and weight vector is w1, w2 and w3. So this is the weight vector. So what is the formula for the calculation of net input? Because what is asked? Net input is asked. What is the formula for calculating net input? It is nothing but summation of I equal to 1 to n xi wi, right? So if I abbreviate this operation, then what is my formula becomes? It is nothing but x1 w1, x2 w2, x3 w3, like this it comes. So if you substitute the value x1 0.3 and w1 0.2, x2 0.5 and w2 0.1 and x3 0.6 and w3 0.3. So if you do the operation, finally I will come at 0.007. This is the way you need to calculate the net input, and this net input calculation is without bias. In case if bias is there, then what you need to do? You need to add a bias B in the formula. Other things are very common. Other things are common. That is what just explained. So this example is what about? This example is explaining the neural network operation, that is particularly MP neuron model with bias. So where is the bias in the architecture? If you look at it, the bias is given like this. So the x0 is 1, that is standard always. The bias value may be changed according to the output of the network model, right? So this is the way in which the operating principles of MP neuron has to be studied. That is how the net input is calculated, maybe with bias as well as without bias. Now it is the turn to understand how the output is calculated. For calculating the output, what do you need? See, I already said that if you draw a network model, you need two operations. One is summation, the other is threshold. Threshold operation may be happen with the help of a delimiter, that is one which is need to check the value, or you can have some activation function, binary sigmoidal function. Let us take for an example here, for which you need to understand the expression for binary sigmoidal function, that is nothing but 1 by 1 plus e to the power minus y in. What is y in? Minus y in. What is y in? Y in is nothing but net input. So first what you have to calculate? You have to calculate the net input, for which you know the formula. Since this architecture contains bias, you need to add the bias B to it. So y in is equal to B plus summation I equal to 1 to n xi wi. So after this calculation of this net input, what you have to do? You have to substitute this net input value into the expression of the binary sigmoidal function. If you substitute it and if you calculated it, finally what you get is 0.625. So this is the way you need to calculate the output of the MP neuron. So followed by calculating the net input. So next, how an AND gate or any logical can be realized using MP neuron, for which you need to know the truth table. So this is called truth table. We have two input x1 and x2, right? X1 and x2, and we have an output y. So if you know the logical gate truth value, if you substitute 1 1 you will get y, if you substitute 1 0 you will get 0, 0 1 you will get 0, 0 0 you will get 0. So this is the way you need to understand the truth table values as well as its output. Now in order to implement this AND function, we need to calculate the corresponding output according to the net input formula, right? First we need to understand the net input formula when 1 1 is substituted. Let me take some other color pen. So if you could see that I am using the first value 1 1. If you substitute 1 1, what is my net input? 2 after substituting in the formula. If I give 1 0, my net input is 1. Likewise, if I give all the other inputs, my values are like that. If you observe this pattern, for 1 1 it is 2, and for other values it is 1 1 and 0, right? So what I can do in order to make the threshold value, I can set the threshold value as theta equal to. If you doing so, then we may get this for the value greater than or equal to 2. For the value greater than or equal to 2, I can get it, and for the value less than 2, I will get 0. So this is the way you need to calculate the working example of an MP neuron, particularly for designing any logical gates. So that is the idea behind understanding the MP neuron. Let me come to the next model, HEB. So next, after the invention of or studies of the two scientists Mekula and Pitts, there comes the Hebb, another scientist, who is the one who is observed the learning that is taken place in human brain. In the very introductory slide itself, I said to you that what is meant by learning? Learning is nothing but weight updation in the neural network. So the Mekula and Pitts didn't study about the weight updation process. That means they didn't study about the learning process. They study about only the way in which input informations are getting accumulated and the outputs are produced. They don't even know about what is meant by weight, what is meant by learning. So those things they are not conveyed by those two scientists, Mekula and Pitts. Later Hebb only have observed that the learning in human brain takes place by means of the synaptic gap. So I already told you what is meant by synaptic gap. There are dendrites. The dendrites are coming and get connected to the axon. Where it get connected to the axon, there is a small gap is there. So the synaptic gap is the one which understand the way in which we have to accumulate as well as the production of output. So in such a way you need to understand. So in the introductory slide, what I said is for each model what you should understand is you need to understand the architecture, we need to understand the net input calculation, you need to understand the output calculation, and you need to understand the weight and bias updation, right. These four things are common for all the architecture. When coming to Hebb network, the architecture seems to be same. So what seems to be same with regard to Mekula and Pitts model. So what is the architecture? It is a two-layer model which consists of input nodes that may be x1 to xn and a single output node. So this architecture is common here also. And net input calculation is the same that we have discussed in the Mekula and Pitts model. So what is a new thing that is introduced here is weight updation. What is weight updation? That is a new weight that we are going to determine is nothing but old weight plus that product of that means a change in weight. So what is change in weight? It is nothing but del W. How that change in weight is calculated? The del W is calculated nothing but a product of xi and y, that is product of inputs with the corresponding output, right. So for what kind of network or what kind of data this network is very popular? This network is very popular among the bipolar data that contains -1 is one side and +1 is in the other side. What is the application of this Hebb network? This Hebb network is very popular for conducting the task like pattern association, classification as well as clustering. So here what you need to remember is architecture is similar to Mekula Pitts. Net input calculation is similar to Mekula Pitts, even it is bias and without bias. The new thing that is introduced is weight updation. Weight updation formula is very simple formula. Old weight is equal to new weight plus change in weight. Likewise, new bias is equal to old bias plus change in bias. So how to calculate the change in bias as well as a change in weight has to be calculated. So change in bias here it is not mentioned exactly, that is change in bias is del B is equal to y, right, this change in bias. So this is change in weight xi y and this is change in bias. So change in bias is always represented by del B as well as change in weight is represented by del W. So this is what Hebb network. Using Hebb network we can realize the AND gate. So in Mekula Pitts model, if you remember the presentation as well as the slide, you don't have any thing about the weight and bias values. So straightly we focus on the way in which the output is produced based on the net input. Accordingly we need to fix the threshold value theta. But here since we have the weight value, the weight values are updated over the period of time. So we need to think about how the weight updation process has been carried out in an iteration by iteration. So in order to understand that, when the problem is given here, see since here it is a bipolar data, we have the binary values, see 1. So inside the place of 0 we have -1. So this is the two different scenarios. That is working example of Hebb net. In order to understand that, let us take the example of realizing the AND gate. So for which the truth table is there. Since the architecture is displaying the bias inclusion, so we have x1 is another input, that input is a constant input, so why, so that we will give 1 as always. So initially when you thought that the W1 and W2 is equal to 0, including the bias, we start with the 0 as the initial value, then we proceed with. So if you substitute the input value and if you calculate the change in weight value, the change in weight value is W1 new equal to W1 old plus X1 Y, right. So then what is that new value? That is 1. Accordingly W2 new equal to W2 old plus X2 Y. So what is X2? You know that what is X2, you have to take it here. X1 is this one, X2 is this one, and 0 is for X0, right, and Y is this one. So we have to calculate all these 3. Accordingly, what is the change in weight value? The change in weight value del W is XY Y. So you have to calculate the del W 1 and 1. So what is the initial value? W1 is equal to 0. How the weight value is updated? According to the principle of the Hebb model, W1 is equal to 1. That is the old weight 1 value, and this one is the new weight 1 value. Accordingly, del W2. So W2 is initially taken as a 0 and the change in weight value 0 and the change in weight value is going to be 1. Likewise bias also. So this is the way you need to understand the learning process in the neural network model. It is nothing but weight updation process. So likewise, if you keep on doing that for several categories, so in this case the first 3 values is taken, 1 1 1 is taken. For second set of input 1 minus 1 minus 1. So if you take for all this thing and if you put a matrix of for this 1 1 1 what is the weight value, this 1 1 1 what is the weight value and what is the change in bias value according to the new weight value, and for all the cases. Likewise you have to tabulate the idea of weight updation process, and this weight updation process has to be carried out until you expect the desired results. There is no calculation of error and all, and this will be dealt in the some advanced model. So this is what Hebb network is all about. Next comes the perceptron model. As I said, what do you need to understand? You need to understand 4 things. One is architecture, second one is net input calculation, third one is output calculation, and the fourth one is weight updation. So the net architecture is same with and without bias, what we have discussed in the Makula-Pitts model, as well as the net input calculation is also same, what we have discussed in the Makula and Pitts model. But when you coming to the output calculation, the output calculation should be, if the threshold value is greater, then it is 1, if the threshold value is lesser, then it is 0, and it is minus 1 if it is a negative value, like that. If it is it goes in the, because this is also going to dealt with bipolar input, right. So what is the formula that we need to understand from the weight updation? So weight updation is new weight is equal to old weight. What is that? Change in weight value. What is the change in weight value? They have given this del W, they have given us alpha T x. What is alpha? Alpha is the new parameter introduced by perceptron network, and it is nothing but learning rate. What is learning rate? The rate at which weight updation has to be carried out. Whether the weight updation has to be carried out with a small increments, or the weight updation has to be increased steadily from one point to another point, those things have been dealt with alpha. This alpha is nothing but learning rate, right. Next T is nothing but target. T is nothing but target. So target is nothing but the actual output that we want to produce. What is X? That is nothing but input. Input is the one that we supply to the network model. So what is the bias? Bias is nothing but del B is nothing but alpha into T. That means alpha is the learning rate, T in the target. So the one new thing that is introduced by the perceptron model is nothing but the learning rate, and the change in weight value should be the product of target and input value. So this is what in the perceptron model. Next comes the another model, adaptive linear neuron, that is ADALINE. So what you have to understand? You should understand the architecture. Coming to the architecture seems to be the same like the feed forward neural network architecture. Right. So what is the thing that is here is, here you need to calculate something like an error, right. So what is an error? Error is nothing but target as well as the difference between the target as well as the net input. So if you calculate the difference between the net input as well as the target, then it is going to be the error. According to the error, the weight updation has to be carried out. So the ADALINE has given all the things with respect to the weight updation process, that is little change with respect to the perceptron. What is the change? In perceptron model, they have given the equation as alpha into t into x, but here what is, instead of only the target, we should take the error. How this error is calculated? T minus net input. So this is the way the error is calculated. So what is the change in weight value? The change in weight value is alpha into t into a. What is the bias? Bias, we have to take only this quantity, So this method is very popularly called as delta rule or least mean square calculation, or otherwise called by the name Woodrow-Half rule. So this is a very popular formula. So coming to architecture, it is same. Coming to net input calculation, it is same. Coming to weight updation, it is same. And what is the change? It is nothing but how to calculate the change in weight value. The change in weight value del W is equal to alpha into difference between the target as well as the net input multiplied by the net input, right? Individual input. So this is the Adeline model. Next comes the another model, Madeline model. By the name implies, it is multiple adaptive linear neuron architecture. So here is the change with respect to the McCullough-Pitts model, with respect to perceptron model, with respect to Hebb model, and with respect to Adeline model. What is the change? All the four models that we have seen just previously are going to be the two-layer model, that is input layer as well as output layer. In the Madeline architecture only, one more layer is introduced. Those things is called by the name multiple adaptive linear neuron. So when you look at the picture, so in the architecture, this is going to be the input layer, and this is treated as the hidden layer, and this is treated as the output layer. There are three layer model, L1, L2, L3. So what you need to do is, in order to understand the operation, you need to consider this first L1 and L2. This L1 is treated as the input layer and L2 is treated as the output layer. Accordingly, you should devise the calculation. That means first you need to divide this node into two halves. Here net input calculation calculated, then the threshold value. So net input is nothing but this net input value, right? Likewise for all the other nodes. And in the second stage, you need to treat this L2 as the input node and this L3 as output node, and you have to calculate the input output. So how this calculated? This is treated as a net input calculation and this is treated as a activation function calculation. So this is the way you should understand the operating principle as well as the architecture of the Madeline neural network model. So coming to the equations, so what is that in the equation? So architecture is different. So since the architecture is different, the standard calculation is same, that is the summation calculation is same and activation is same, but the formula is you have to do it in the two different phases. First between L1 and L2, that is the input layer and hidden layer, by keeping the hidden layer as output layer, and next is between hidden layer and output layer, and by keeping the hidden layer as the input layer. So in the overall picture of this Madeline training algorithm, the hidden layer plays the two role. In the first phase, it acts as the output layer. In the second phase, it acts as the input layer. Accordingly, the calculations are carried out. So what is the formula given by Adeline model? That is we have to calculate the error, and that error has to be multiplied by the term. If you look at it here, you can understand that. Look at it here, you can understand that. But it has to be calculated in the two phases. In two phases, you have to calculate the algorithmic calculations, especially for weight updation as well as for bias updation. This is what the Madeline training algorithm is all about. Next, an important problem that you should understand. Why this problem you need to know is the widely used neural network model is, you all know that backpropagation neural network model. So you should know where this backpropagation came into picture and what is the need for this backpropagation in change. If you observe all this architecture model, that is McCullough-Pitts, Hebb, perceptron, Adeline and Madeline model, what is the unique in terms of architecture? Madeline only changes, that is in terms of number of layers. Otherwise all are feed forward architecture having two layers, right? Input layer and output layer. And in input layer you have n number of nodes. Yes, particularly with the Madeline model you have hidden layer. Hidden layer also you can have n number of nodes. So both the input layer you have n number of nodes, and both in the hidden layer you have n number of nodes. But when you talk about the similarity among all these models that we have discussed so far, the output layer contains only one node. So here you need to take a challenge that what if I have more than one node in the output node? When you need the possibility of having more than one node, if the number of output categories is more than 2, then it is going to be 2 nodes or 3 nodes in the output layer. So what is meant by linear separability problem? If you look at the slide, there are some objects that are being plotted in the xy plane, and if you could see that there are 3 different kinds of shapes are there, right? If you could draw a straight line like this or like this or like this, if a single straight line is able to separate this object like this, right? So this straight line separates these 2 objects from this object. This straight line separates this object from these 2 objects. This straight line separates this object from this. Likewise, if you drew a single straight line, or if this straight line is sufficient enough to categorize the patterns, then this problem is going to be called as the linear separability problem. But what we have and what we face actually is, if you look at it, most of the real world problems are non-linear in nature. I will discuss about the word non-linearity in very detail in the subsequent presentation, but as of now you should understand that the task of categorizing the or separating the data into different classes may have non-linearity also. In order to solve this non-linearity, what are all the models that we have seen so far, like Maculapits, Hebb, Perceptron, Adeline model are not sufficient enough, and you need to go for one more model, and that is be a widely accepted model which contains many layer architectures, input layer, lot of hidden layers, as well as the output layer. And but particularly in the output layer you have more number of output nodes rather than having only the single output node. So let me explain this linear separability more in detail. So let me take the OR gate. So say for example, if I want to design OR gate, what are the output patterns? If I give input as 0 0, my output is 0. If I give input as 0 1, my output is 1. 1 0 1 and 1 0 1 1 1, right? So I have 2 categories, right? 2 classes. One is having class 0, this is the first category. Another one is having the class 1, that is the second category. So if I plot this in a xy plane, so what I get is, so I get this one, second category, that is represented in the pink square box, and this 0 is represented in the orange color solid balls, right? So now this problem is a linearly separable. Why? This is belonging to category 2 and this belonging to category 1. So by means of a simple straight line, I could be able to category the first one with the second one. So for these kind of problems, our Maculapits, Perceptron, Hebb model, Adeline model are sufficient. Even Adeline model also you can go, suppose if that problem is a little complex enough. Likewise, if we take the case of AND gate, the AND gate is something reverse, right? See, for example, here if you take, this is category 1 and this is category 2, right? So category 1 is 0 and category 2 is 1. If you plot this with respect to xy, with respect to x1 and x2 plane, for 0 0 you got 0, for 0 1 you got 0, and for 1 0 you got 0. So these are all here, right? And for 1 1 you got here. So again, for this particular example, if you do a straight line, then this straight line also categorize the zeros and with ones. But when coming to the XOR gate, if you plot the values likewise for OR gate and AND gate for 0 0 1, right? So that means 0 in the xy plane, 0 in the x1 plane, and 0 in the x1 plane, that gives this square, that is a pink square. For 0 1 it is 0. So 0 in the xy plane and 1 in the x2 plane, this gives this orange. And third case 1 0, 1 in the x1 plane and 0 in the x2 plane, that gives this orange, right? This is second. And 1 1 is nothing but 1 in the x1 plane and 1 in the output plane, that gives this square. Now I cannot categorize, this is belongs to second category and this 2 belongs to first category and this belongs to the third category, so second category, sorry. So now if you could see that there is overlap and there may be a lot of non-linearity is there. So a single straight line is not enough. Say if I drew a straight line here, then the 2 objects are mingled. If I do a straight line, then the 2 objects are mingled. Then I give a straight line, then the 2 objects. So I cannot give you a clear straight line, clear cut straight line, so that it exactly divides one object, one category of object with another object. So this kind of problem which always needs a non-linear line which exactly divides the given samples is nothing but non-linearity problem. And of course most of our real world problems are non-linear only, for which we have to go for a backpropagation neural network that we will see in the next presentation. So what we have discussed so far, as a summary, we will discuss the Mekula and Pitts model, Hebb model, perceptron model, Adeline model and Madeline model. For all the models what we have discussed about architecture, net input calculation, output calculation, as well as weight and bias updation. For Mekula and Pitts model, there won't be no weight updation because he has not observed the learning process. Starting from the Hebb only, learning process has been observed. And what is the difference in these kind of model, that is Beck model, Hebb model, and it is nothing but change in weight is nothing but xi y, change in weight is nothing but alpha tx, change in weight is nothing but alpha into t into z in j. That means each layer is calculated, right? So this is the three changes that has been incorporated. In case of bias, it is y alpha t, and it is nothing but alpha y into. So this is the three changes that is observed. So only in the calculation of del w as well as del b, these models are differing with each other. Otherwise the models are common to one another, both in terms of architecture and other net input calculations and others kind of stuff. So with this we come to end of this presentation, and in the next presentation we will dealt with the nonlinear separable problems and how the nonlinear separable problems can be solved using a backpropagation neural network. I thank you.